we're going to talk about defining the ionization energy and predicting the trends in those in the periodic table. Defining electron affinity, subtly but importantly different from ionization energy, and predict those trends on the periodic table. And understand the trends in metallic character in the periodic table. Those are the three related topics we're going to talk about now. Okay, so ionization energy. This is super important because it relates to how easy it is to pull an electron off of an atom. So when we're talking about reactions, that is pretty key. Now, electron affinity we define for a very particular reaction, and that is if we have a gaseous atom and we strip an electron off of that, what is the energy that that takes? So for example, for hydrogen, there's only one ionization energy because there's only one electron to strip off, and that is 1,312 kilojoules per mole, which you might have seen that, remember seeing that number before when we talked about the different atomic spectra. That would be the energy to go all the way from the ground state, the n=1 state, to strip it off all the way into the n=infinity state, where it is essentially free to move around. Obviously, most reactions don't involve a gaseous atom and stripping off the electron, but we can use, we can connect other reactions together. Remember, enthalpy is a state function. So if we have this particular reaction that doesn't happen very much, we can connect it with the energies involved in other reactions and actually construct the energy, total energy change and enthalpy change in reactions that do actually happen. So just so we have a consistent way to define how much energy it takes to rip an electron off, we define it in the ionization energy in terms of this particular reaction. Gaseous atom, strip off an electron. Okay. So yeah, everything is gas phase. Gas phase, H+, gas phase electron. Obviously, usually in a solution, you have other things going on, but we can take into account by looking at other reactions. All right, so let's look at the ionization energy. So there's clear periodicity to the data with maximum value for the noble gas elements. You can see that it's very hard to strip an electron off of the noble gases. And it's pretty easy to strip electrons off of the alkali metals. Now, one important thing to notice here, it always costs energy to strip electrons off of a neutral gaseous atom. You might think, oh, well, but doesn't sodium like to lose its electron? No, it doesn't like to lose its electron, but it likes to lose its electron. It doesn't care about the electron nearly as much as other atoms do. So it's always a tug of war. Yeah, you actually have to expend energy to get an electron off sodium, but you can gain a lot more energy by having that electron go somewhere else. So that's the key, it's this tug of war. So no neutral atom likes to lose an electron, but some like to lose an electron a lot less than others. Noble gas really doesn't want to lose that electron. So why? Why do we see this pattern? So across each row, electrons are coming off an orbital with the same n, but the nucleus is more positive. So as we go across a row, from lithium to neon, then they're all coming off of 2p orbitals. But, and so those 2p orbitals are roughly isoenergetic, but the nucleus is more positive. For lithium, that n=2 electron only has to get away from 3 neutrons, but for neon, it has to get away, wow. Why do I keep saying that? Has to get away from 3 protons, but for neon, it has to get away from 10 protons. So that's a lot more to pull. Even taking into account the shielding, there's still a lot of positive pull that it has to get away from. Okay. Yeah, so it's harder to pull a 3p electron. And if we just look at, compare argon with chlorine, it's harder to pull a 3p electron off an atom with 16 protons than 15. Actually, that's with comparing sulfur and phosphorus. So if we compare sulfur and phosphorus, then it's harder to pull. Yeah, it's going to be harder to pull that 3p electron off from sulfur than from phosphorus. There's some exceptions to the trends here. Usually, think as you go across, then it's just going to keep on going up because you have more and more protons as you add things on. But we notice a few weird trends here. So the general principle is it's easier to take electrons off if the ions are more stable. If you go to an unstable ion, it's going to take a lot of energy to get to that. It's going to be easier to take it off if you leave a more stable ion. So if we look at these ions, if we look at B+, which is what you get after the first ionization energy, that has a full subshell. And so that's actually not as bad. You have a filled subshell. It's not bad as bad to take a proton, take an electron off. If you look at oxygen, that drops down to a filled half subshell. Aluminum, you are dropping down to a filled 3s subshell. And so those are slightly more stable. The trend reverses a little bit because you have filled subshells and filled half subshells that stabilize those ions. Okay, so far we've been talking about just the first ionization energy, but clearly we have to get other ions off as well. We have to get other electrons off as well to create like magnesium 2+, for example. So if we look at what the first ionization is, we'll be taking for magnesium, we'll be taking off one of the 3s electrons to leave one 3s electron out there. That is not so hard to take off. Magnesium 2+ will be taking, that's the second ionization energy. That's the energy involved in taking that 3s1 electron off. But then the third ionization energy of magnesium, we're going to be taking off a 2p electron. We're no longer taking off those weakly attached 3s electrons. We're taking off the n equals 2 electrons, which are much closer to the nucleus. And so if we actually like pull up the numbers for some of these things, the first ionization energy is 737 kilojoules per mole. The next one, it is more energy, but it's about the same magnitude, 1451 kilojoules per mole. But the third ionization energy, when we start pulling off the 2p electrons, is 7,733 kilojoules per mole. So the first two are about the same magnitude, but the next one down is just really hard to pull off. And that is why we generally just see magnesium 2+ ions. We don't see magnesium 3+ ions in most chemical reactions because it's really hard to get that electron off, because now we're pulling down in the 2p